Hello and welcome to the McHale Report podcast. My name is John McHale, Group Editorial Director with Military Embedded Systems and host for today's event. Our guest today is Jason Ferguson, President of W5 Technologies. And today we're going to cover the Mobile User Objective System, also known as MUOS, and how it fits into the defense industry, the technology behind it, and design trends that are supporting it and making it more modern. So let's get started. Jason, welcome. And to get us started, can you tell the audience a little bit about W5 Technologies and your role in the company?
Yeah, first I wanted to say thanks for having us on, letting us talk about MUOS, which is definitely something we're very passionate about here at W5. So first, myself, I'm Jason Ferguson. I am the president of W5. As we're a small company, that means I wear multiple hats. So it can be everything from sales and business development and helping out on engineering challenges to changing the light bulbs in the office. It can be anything. So W5, our core competency is cellular and modified cellular. So we're unique in that fact that the vast majority of our staff has come out of the old telecom companies that we used to have. So myself out of Motorola, and the vast majority of my team now is ex-Motorolans. We built CDMA cellular infrastructure. Some of them had worked on Iridium. Some of them, after I had left Motorola, continued on with the LTE stuff. But basically what we target is very hard and challenging wireless products for the DoD market. Our main focus right now has been on MUOS technologies. So we're the only maker of a MUOS simulator for the satellite and the ground system. Beyond that, we have just launched our MUOS Gateway product, and we've been attempting to deal with some of the coverage challenges that the system have, and we'll get into some of our other products that we've been working on as we go. But yeah, it's exciting to be here. And
Well, when we first met, you talked about MUOS, and I was like, I haven't talked about MUOS in a while, and that would be a good subject for a podcast. So can you give the audience a brief history of MUOS, its place in the defense industry, and how it differs from other MILSATCOMs systems?
Yeah. So MUOS fills the narrowband SATCOM role within the Space Force's arsenal of satellite communication systems. So the primary mission of MUOS is for the dismounted soldier. So and we'll go a little bit into the history of narrowband SATCOM. So it's been around for decades. I think going back to the 60s or 70s, we've had a capability of narrowband SATCOM. So the purpose of it is, if you think of it, the curvature of the Earth, basically if we had two people standing with walkie-talkies, the most we could see is 22 miles. And then the curvature of the Earth gets in the way. So for our military, we need to talk beyond 22 miles, so we need something or some way to get that RF wave to carry. We use satellites. Specifically, MUOS uses geosynchronous satellites. So the satellites are 22,000 miles away from the surface of the Earth, rotating around the equator. Now, traditionally, the previous versions of narrowband SATCOM kind of went from the original basic, I think of it like a ham radio almost, where the satellite in the sky was a big repeater. So it listened on a frequency and then chirped back the response on another frequency. So everybody could hear what you were saying. And then to add capacity, we went to a DAMA system, and that was like TDMA. So we're using time to share the frequency to give us more capacity. Well, then MUOS shows up and just blows it out of the water. So 10x more capacity than the previous system. But with 10x capacity gain, there's no free lunch in wireless comms. So we end up with additional complexity to get that extra capacity. Now, on the previous generation system, the user had to stop. So the system's for the dismounted soldier. He's got a man-pack size radio with him, and he has to stop, deploy a little dish, and point it at the satellite, make his call, fold it back up, and then start moving again. So one of the main requirements for MUOS was on the move. So I want that SATCOM communication, but I want the soldier to be able to move while he's talking. And a good example in a movie of the legacy way of doing it is the movie Lone Survivor. There's a scene about 3/4 of the way through the movie. They're being chased, our soldiers are being chased by the bad guys, and you see the soldiers have to stop, pull an antenna out of their backpack, open it up, and then point it. But they had to stop. So the first challenge was, how do we get the terminal to actually move with the soldier? Whether he's on foot, in a vehicle, on an aircraft, MUOS works in all of those scenarios now. So in the acronym that MUOS stands for, a lot of people think that the M stands for Marine User Objective System, because the Marines love this system. They have adopted it. It's in their PACE plans, but the M actually stands for mobile. The mobile user was the goal. And it has to be small. So if we look at like the wideband systems that the Air Force also has, those dishes, the terminals on the ground, they fit in a transit case, or they're mounted to the back of a trailer. So you need all of this power. You need a generator or a big battery bank. You need time to set the dish up and get the link up. MUOS isn't like that. It was an attempt to bring a cell phone-like experience to the dismounted soldier. So just right off the bat. Now, the other benefit of MUOS specifically for narrowband is the frequency range we use. We're down between 280 and 380 megahertz. So the wave, just the frequency that we're in, that wave carries and penetrates more than your commercial cellular systems, more than Starlink, more than anything. So for the dismounted soldier, one of the requirements was triple jungle canopy. So I am in a jungle. I have all of this ground cover, all of the stuff in between me and the satellite, and we still have to operate. Where most other SATCOM systems are, I need a clear line of sight between my terminal and the satellite.
So it's been around a couple decades. You took it from when it was a basic technology to where we are today. But what about modernization of it? Is there funding for it? How are we going to upgrade the systems? Where does it look like within priorities within the DoD?
So let's just set the scale of, because I think I was watching some of your other podcasts, and especially on the topic of MOSA, and how do you do that, especially with a system as unique and bespoke, if you will, that MUOS is. So the way MUOS was constructed is the program purchased a 3G cellular network. And for most people, they're not going to understand what that actually means, because the user experience with our commercial cell phones is so seamless. It's so smooth. You don't need to know anything about that network. You just pick your phone up and it just works. You can go check your news or make a phone call. Behind the scenes, there are many, many, many engineers working to make that network work for you, so you don't have to care about it. It just works. So like, of this generation of cellular network, I worked on the CDMA systems at Motorola, but that organization was about 10,000 people to produce a version of similar to this network. Well, MUOS started with that input of, an organization of 10,000 people built X, and then another organization of, let's say, somewhere between 1,000 and 3,500 people went in and modified it. Because now we're taking something that wasn't meant to talk beyond like 50 miles, and we want that terminal to be away from that ground system 44,000 miles. So we're not in a sustainable way, but if we set out on day one to build it in a sustainable way, it would have never been built. You know, the upfront cost was so high that we had to take that risk, knowing that we would have to deal with the sustainability at a later date. And where we are now is dealing with that sustainability challenges. So some of the boxes that are very componentized, if you will, and I'm not talking like a specific board, but a box. We'll just say a box, and we know the innies and the outies, and we know what the box needs to do. So they have cleaved off that and have gotten another company to come in and do a replacement. But really that heartbeat of MUOS, that cellular network, the last effort I saw to kind of reach out to industry for proposals on how to sustain that or modernize it was in 2022. And I don't think the DoD saw what they were looking for, so those efforts didn't continue. But as with anything, time's not friendly to hardware. The hardware is still getting older every day, and because of the complication, starting sooner than later is better because it gives us engineers more runway to solve the problems.
Well, thank you for watching all of my podcast. God bless you.
Yeah.
I appreciate that. We're always looking for more fans. But when we first met and we kind of talked about MUOS, you made a comment that MUOS kind of gets a bad rap as unnecessary expectations of 5G capability were placed on the technology. Can you elaborate on that and maybe share some of the other misconceptions people might have about MUOS?
Yeah. So to set the stage for the viewers, everybody hopefully is still familiar with JTRS and that program.
Yes.
And everybody has different opinions on it. And I know my opinion on it has changed. It's softened as the years have gone on. And I think it's really I've understood the gravity of what they were trying to achieve, and to push out something as ambitious as JTRS required changes the primes, changed the way the government did business, and it was all happening all at the same time. But the purpose of bringing that up is MUOS was built in that time frame, and the terminal software, the MUOS waveform, was produced under that JTRS model. To my knowledge, it's the only waveform from that era that has survived. So any other waveform that was made new for JTRS has gone by the wayside and replaced by something else, except for MUOS. So MUOS made it out of the jitters environment and was successful and is being used. So where I think we got a bad rap is the ground system and the satellites were deployed like in 2011, 2010. I'm sorry, 2011, 2012 timeframe. But there were no terminals available to use the network because we had to jitterize the waveform. So we had a version of the waveform, and then we had to jitterize it, which was add a lot of security features to an existing waveform. So that kind of put us behind schedule a little bit. And then because of that jitters model, it's not once we get one radio working, that's what everybody's going to use. That software then needs to be rolled out across all the terminals, all the software-defined radios that are going to do MUOS. So we're taking an incredibly complicated system and then having to train, for the most part, every large defense prime that makes a MUOS terminal on the in-depth workings of this, which it just takes time. Fast forward then to 2018, and we failed the first MOT&E. So now the government has deemed that it is not ready for operations. And we won't go into what those findings were, But what it did is it put the MUOS community back 3 years, because once you miss your MOT&E window, it's not like you can say, oh, that was a couple of bugs and we'll be ready in 2 months to rerun the tests. You start that cycle over again, and now it's 3 years from now you can retest. So I think people got frustrated because they're palming for money to get MUOS onto their platforms and into their soldiers' hands, and now all of a sudden we hit a gap of 3 years. So then everybody's like, well, I need to go find something else. And then finally we get through that. The system's live, it's rated for operation. We've got MUOS terminals now. And this is like, I think 2018 is when we passed MOT&E. So it was like 2016, 15 is when the failure happened. And then the first thing that the soldiers hit with is, this thing does not function anything like my previous SATCOM terminal, like not even close. So from the soldiers' perspective, what they were used to was, I had my man pack, I got my channel, I flip the switch, the radio powers on, and I can grab the mic and key it up and start talking instantly. That's what they were used to. Well, how long does it take for your cell phone to boot? Takes a bit. It's got to register with the network. So right away, the user experience wasn't it's not great, that initial learning curve. So now all of a sudden the soldiers are like, well, now I got to wait for this to register, and it takes, a minute. And then I got to download these config files, and then that's 20 minutes. And then I can start my mission. And I needed this extra computer to provision the radio, and I needed to get something from this guy and this guy and this guy, and I got to get all these keys. And so all this stuff to make the security happy is now an additional load on the soldier just to get the radio going. So everybody's frustrated because it's not, everybody's expecting this because somebody's been holding it up on stage saying, we're delivering you this. And then they get the terminal and you're like, I got to be a PhD to configure it. But, and the Marines really set out hard. They figure that out. They get processes and procedures, and now they're on the network. So now you're on it, and everybody's used to 4G, 5G systems in our lives. Well, MUOS data isn't, it's dial-up modem speeds from back in the 90s. So the data transfer isn't as great as we would like today. By today's standards, it's not keeping up. Because of the constraints of the system, though, if you think about it, how did the commercial cellular providers provide us that faster speed? Well, they moved to LTE. And that doesn't mean that WCDMA is bad. It's just WCDMA ran out of runway to hit the new requirements coming, which was greater bandwidth. There's only so much information we can carry across an RF wave. And to really get these great speeds, we need more bandwidth. But we don't have more bandwidth. We're stuck. Narrowband SATCOM has this set amount of bandwidth, and we're not going to grow it. So we just need to use that more efficiently. But, so the flip side was, it was the delays, plus the cumbersome way to provision the terminal. And once you get over that hurdle, but at that point you're kind of mad at it, you get over that hurdle, and what's the first thing everybody notices? Crystal clear voice. MUOS of that era, cellular of that era, voice was king. So when MUOS was spec'd out, the cellular industry itself was really at this crossroads between voice being the priority on those networks versus data. And that transition didn't happen really until the iPhone hit the market, which was 07, 08. So MUOS started being built in 04. So we're already on a track. and then the industry changes mid build. And if we were to go and grab some of those things that we were seeing in the industry, that would have been scope creep. How do you stay on track and on schedule if you're constantly grabbing stuff from the market as it moves? So for its mission, voice was really the goal, because when we started building it, voice was the largest demand in networks in general. Military was no different. So now, to kind of bring it up to current day standards, it's never going to be a 1 gigabit a second system. It's just, we don't have enough spectrum to do it. And really, MUOS focused on giving capacity, more users, because pre-MUOS, everybody, the complaint you always heard from everybody was, I can't get a SATCOM channel. You had to be a very high priority user to get one of those coveted SATCOM channels. So the Marines, they never had SATCOM channels. They were too low on the food chain. And now MUOS rolls around. MUOS can support hundreds of thousands of people. Marines are like, we can upgrade every radio, and boom, they got 30,000 SATCOM channels all of a sudden. That's incredible. And the other thing then that we kind of take for granted today is on those legacy systems, the beam was very wide from the satellite itself. But you could only talk to other people within that broad beam. MUOS, with the cellular back end, you can be standing in India with a MUOS terminal and call somebody in Alaska or call somebody in Hawaii. I mean, the infrastructure behind the satellites basically takes care of all the ground routing for you. So it's got some very advantageous features, but if you approach it and think like it's going to be your 5G phone, you're going to be disappointed. That plus the additional of latency, just because we're going out to geo, it it all rolls into the perception of the system.
So back to what you're talking about earlier, with MOSA, it's not really an easily upgradable system. It takes time to prep and prepare this for each generation. It's kind of what I'm hearing. It's not really it.
Yeah. And I forget, the gentleman you just had the podcast with a couple of weeks ago.
Oh, yes, from Rochester Electronics on aftermarket supplies. Yes. Dan Dees.
So I was listening to him, and I'm like, wow, what this guy's doing is absolutely incredible. I'm like, how did he figure it out? Because I know we haven't figured out what he's able to do. So I'm listening to him talk, and then he gets to the point where he's like, unless we're talking about RF systems, then none of this applies. And I was like, there it is. So okay. I'm not crazy. So the need of us building real-time software, especially for communication systems, we're eking everything out of that hardware as humanly possible. So when we go to move processors, that code base was really written for that particular processor. And then when I have to go move, I have to do some additional development to move that component. And you could say, well, let's just say an FPGA, for example, and I'm going to live within the Altera ecosystem. But I wrote something for an Altera FPGA today, and then 15 years later, I'm like, I need to move it to another Altera FPGA. Is that going to move cleanly? No, not really. And then even if you start talking about moving between vendors of FPGAs, now those proprietary IP cores, those are different between vendor A and vendor B, and it could be a rounding issue is different. So you have to take account for it. So yes, MUOS has a very hard problem with moving off of the original system onto a next one. But that's okay, because W5's been working on that problem actually since 2012. And we'll get into that when we get into some of our products.
So when it comes to testing of equipment, I understand the government's going to be shutting down some of their labs. and why are they doing that? And what options will users have for testing and troubleshooting MOSA systems, MUOS equipment?
MUOS systems. Yeah.
Yeah.
So
Will you guys be
because
one
of,
of the options? Is that
yes,
something
yes.
okay.
So we provide actually the only option. So how did we get into this spot in the first place? So once again, we have these large proprietary cellular systems of that era. And when I say that of that era, what people need to understand is these are refrigerator sized boxes. We didn't even have multi-core processors back then. So all of this magic is happening on single core processors from like the late 90s, early 2000 era. The challenge of a cellular provider is they needed to deal with all that sustainability, but they're a moving target. Every 10 years, they're coming out with a new standard, and the cellular providers have to work with their customers, their Verizons and Sprints, to kind of meet up. Here's hardware we need to pull, here's hardware we need to add, but the cellular providers kind of providing that migration path to their customers. Now, MUOS, we bought a snapshot in time. We deployed the hardware, but they kept one unit back, one ground system to test with. And that resides in the General Dynamics Scottsdale lab. And then there was another government lab that ties back to share that equipment. And the original model is people building MUOS terminals would go to these labs, either the government certification lab or the General Dynamics lab, and they would do all their testing. Well, if you've ever tried to develop something remotely, so your engineering staff's on the road actually developing a complicated piece of equipment, that's hard. So what we did is we shrank the entire MUOS network and satellite into a portable transit case, and we call that our Mighty Moose. So vast majority of integration is happening now on our portable ground station. So how we got there is after we got done helping Lockheed and General Dynamics build the MUOS system, we rolled right into building the portable. And this will make sense why we did this, but it was basically we had the knowledge and capability at that time, so we rolled it forward and we started making smaller MUOS ground systems.
So you got ahead of the requirements, knowing they're probably going that way. You kind of went ahead a little bit.
Yeah. So at that point, we had shopped it to the government to say, hey, we think the market's going to need it, but there was no budget at that time to build it. So we started under the SBIR program, but even a phase 2 in SBIR is going to max out back then at like $1 million. And I know people sit there and say $1 million is a lot of money. When building a cellular network, $1 million doesn't get you very far.
Barely get you a bag of groceries anymore,
Yes. So in the other thing to think about it, and it kind of goes into this mixture of cellular meets DoD into a custom system. To deal with specific problems, there's not a one size fits all, let's say, base station or the box that sits below the antennas that we all see in our daily lives. I live in Phoenix, so I get palm trees as my antennas. If you're in Colorado, you get pine tree antennas. But think of it this way, like how do you do a tunnel? How do you provide cellular coverage into a tunnel? Well, your normal cell towers aren't going to see inside. We just don't have an RF wave that's going to penetrate all that concrete. So we make smaller cell sites and stick them up in tunnels or inside buildings or whatnot. So that's the market that we tried to go after because A, we needed, or new people were going to need a way to test it in their facility. And B, we also knew that there was going to be this large problem with sustainment of the system because it was on this proprietary hardware. And even when you look at that, moving that old software off of that system onto a newer system may not really make sense because we're so far off now. If we went back to the original MUOS system that's currently running today and said, I need to refresh it, some of that code, because of the constraints the developers were under back in the early 2000s, don't apply today. So the way we manage that is we knew right away we needed to get on the sustainable hardware, because even building a MUOS in a box, if you will, we know that that box needs to have a 20-year life cycle minimum. And I even thought 20 years was long, but last week I just quoted selling one of our units with one of the legacy units from another company. They wanted us to compare. So even though MUOS has been live for 7 years, people are still buying the old SATCOM equipment. So this like path to upgrade off of a new to a new system, that was part of MUOS's headache. It takes 7 to 10 years to roll those terminals out.
Yeah, that's not a fast deployment of anything.
Yeah, but it's definitely
but it makes sense. There's a reason for that. It's not like you're a cell phone. So
yeah, and so then the other way to think of it is, so you're like, Jason, but you just said MUOS is for the dismounted soldier. 100%. But to talk to that dismounted soldier, somebody else needs a MUOS terminal. So we have to put the MUOS terminal in Humvees and MRAPs, and every naval ships get it, subs get it, every aircraft is getting it. So now theoretically, anywhere on the globe, any soldier could talk another soldier that's got a MUOS terminal. So it speeds up the information sharing chain, but it takes us time to push all that hardware out to everybody, because it's not like a ship you can just show up on a dock and say, hey, here's your new radio, guys, go plug it in. They have to do a maintenance window. And
so, yeah, sorry to follow up on what you're talking about earlier, but the dismounted soldier, are you looking to reduce the size of your systems any further for that? I mean, do you have a product that goes a little smaller, or I mean, the size of the footprint for the capability?
Yeah. So this is and remember, we're not building MUOS terminals. Yep. We're building ground systems. So the ground system out in the field right now, fills, and you can't see my office. It's not that big, but let's just say 3,000 square feet. Fill that with refrigerator-sized boxes, and that's a modern-day MUOS ground system. So we did a research with the Navy, and I'm going to try and show this to you. So this is a lot
smaller than 3,000 square feet.
Yes. So this is as small as we've been able to take a MUOS ground system. And this one was specifically designed for putting it up at LEO.
Okay.
Yeah. So GEO is fantastic. And it's fantastic because we don't get a lot of movement from the satellite. And also, looking back in history, we used geosynchronous satellites because they were far away. So it was the ultimate high ground, is the way I've heard people explain it to me. In the military, we're always looking for the high ground, and a geosynchronous satellite is the ultimate high ground. There's no higher. And then I think a report came out like in 2012 that an adversary had come close enough to be concerning that people may be able to shoot down a geosynchronous satellite. Mm-hmm. And I think that was an eye-opener for people, because we thought that those satellites were never to be contested. So now we're in this proliferation age of LEO. So we don't care if one satellite gets knocked down, because we've got 3,000 other satellites.
Redundancy in the platform itself, so to speak.
Right. So what our approach is, hey, is MUOS the best waveform today? It's filling its mission. Can it be made better? Absolutely. But the soldier has it in his backpack today. And if we know, hey, somebody came up with a brand new whiz-bang system based off of 5G ricocheting it off those satellites. We know it's going to take 5 to 10 years to roll that new equipment out amongst the entire fleet. So what we attempted to do is say, hey, we are just going to make the system better by bringing that satellite closer to you. Then it takes away from the power, because now all of a sudden we're worried about signatures coming off of these soldier radios. It's no good if a soldier is hiding and then he keys up a 20-watt PA and blasts UHF into the sky. People are going to notice that. So, and then the bad guys know where you're at just based on the signature. So lowering that profile would be advantageous. And one of the ways to do that is to bring it closer to the soldier. So we bring the ground infrastructure closer. Next issue then is latency. And so what we've done is, in the current system, the geosynchronous satellite is just what's called the bent pipe. So we tried to not put a ton of smarts in the satellite, no offense to the satellite makers, but basically we didn't want to constantly update software on a satellite. So it ricochets the signal back down to a ground station, and that's where we do all that WCDMA processing. What we did in our shrinking is we put the whole ground system up at LEO. I don't want ground stations anymore. I want the constellation managing it. And what that allows us to do is really deal with the latency problem, because now we don't need to ever hop back down and then come back up to route to somebody. We just manage it all in the sky.
You eliminated the middleman, so to speak.
Yeah. So it makes it easier then for the planners, because then you're not planning, well, where are my ground sites? Are they in the places that we want? Do we need to move them? And it's just all in the network. Now, we will need ground stations to pull that signal back down to the ground. But I mean, what the SDA's been doing with their LEO constellation and providing that transport layer for people, that's awesome. Because now I don't need to build this ground station. They've taken care of that problem for us. They've taken care of the crosslinks for us. So now we can focus on what we're really good at, and that's just that waveform communication from the satellite to the soldier. How the information routes around beyond that, SDA seems to already have it covered for us. And I think that's really going to allow the industry to move faster, because everybody doesn't have to show up with everything every time.
So just two more questions for you. One's kind of a follow-up from the earlier, and speaking of components and shrinking, you mentioned how you were programming on an Altera FPGA earlier today, right? So from your embedded components inside, do you use a lot of commercial stuff like Altera FPGAs, or do you have to make more custom stuff, especially as you move into a smaller footprint? How do you develop stuff yourself there, or do you kind of just buy off the shelf for that sort of thing?
So everything's off the shelf.
Okay.
Everything. And well, no, I take that back. There are very few times, eventually you'll run into an engineering challenge, and the quickest way to solve it is to just build it from scratch yourself. But because of the lead time, the amount of time that we need to keep this system running, the systems that we build, we've had to rely on the commercial industry, because if we said, hey, we need to build custom hardware before we can even start building our software, we would never achieve any of our goals. It's too big, It's too heavy lift. But the amazing part is they're software-defined radios, and industry has really helped us actually exist. So let's say, we don't use like an OpenVPX chassis for our MUOS right now. Mm-hmm. And we had looked at it years ago, and we just ran into a problem where there was a very particular processor we wanted to run, and that wasn't packaged to be in that form factor yet. Now, could I have paid somebody to put that chip on a board and make it slot in? 100%. The industry, they're primed. They do it all the time. It's not an insurmountable problem. It's a cost problem though, because if I'm producing, let's say 6 units a year, I'm like the worst customer for that guy.
Yeah. So they're going to charge you a lot more.
Yeah. And then so for me, what it's really turned into is we're always looking to build in a sustainable way because we are on COTS. And we do know that that's going to shift out from under us constantly, sometime predictably, sometime not predictably. So in general, though, there are long life parts. I forget the actual industry term, but like if you go to Intel, they've got like, here's all the chips that I make this year, and you're going to go to Dell and buy a new laptop and get a new Intel i whatever. In that spec sheet, though, there's going to be like 2 or 3 that says we're going to make this processor for a decade. So that's what I'm looking for. But at the same time, we know we're going to move. So like, and it kind of all wraps back into that sustainment piece. And I was really trying to, after I was watching your other podcast,
I was going to bring that up. Yeah, that's what they do.
How do I explain it? Because when the first time somebody mentioned MOSA to me, it was in a meeting, and I was in a meeting with a bunch of guys from the Navy, and somebody asked me, "Are you MOSA?" I'd never heard of the term before.
You're like, "No, I'm Jason."
No.
Yeah.
and one of the people sitting next to me kind of leans over, and he's like, "I've seen the inside of your box. You're MOSA."
Well, because that means you're using open common standards and open stuff inside your box. That's what he means.
Not 100%.
But that's where I think he was coming from, because what you talked about, leveraging commercial off-the-shelf technology, typically says you're MOSA, even if your end system really isn't.
Right. So, but then as I started reading about it, I was like, yes, we do it. And why is this new for people? Was kind of my next question. Why isn't everybody building like this already? And when you think of it, so I was incentivized to build this way. Well, really 2 reasons. One, it was a hard lesson learned. So it goes back to the Motorola days. And in the late 90s, early 2000s, Motorola ended up creating within our cellular infrastructure division a sustainability problem ourselves. We were rapidly developing new hardware platforms to fit these niche use cases in cellular. But then our software had to run across all these unique hardware platforms. So it like beyond quadrupled the amount of testing for every feature we added. So at Motorola, they were like, once the mess was created, everybody's like, oh, geez. It was very obvious from the numbers what had happened. And then the next part of the career at Motorola was getting to what they called common platforms. So it was from a company standpoint, how do I build sustainably across multiple business units? So I think we just kind of took that going forward and said, geez, how are we going to build a 20-year product on commercial parts that are going to constantly move and change below us?
Sounds like one of the military end user platforms, right? All the electronics in these aircraft got to get swapped out every 6 months, but the aircraft's got to last 5 decades.
Yes. So then I was, how do you write a requirement for that? Which is really hard. I mean, it's incredibly hard. Now, we were incentivized to build in a way because it would just cost us too much to build in any other way. But then kind of looking back at how the original MUOS was built, it would have never been built if we had built it in a MOSA way from day one. So here's what I've learned after doing this, building these technologies for 20 plus years. Everything's always going to move. So usually the first, and I don't want to call it prototype, but the first unit that rolls off is the hard-coded, we just need to prove that we can make this technology work. And that example is the current live MUOS system. But then we started moving right away on the next one. We were trying to fill a different need, but the software is basically all the same. It's the same software stack. But it's not just the hardware components. Your operating systems change, your tools change. So this is something that we still fight in the MUOS world, but back in the early 2000s, everybody was trying to get rid of software developers, just like all the AI tools today are trying to get rid of the software developers. So there was, in the early 2000s was UML was the new hotness. So your system engineer could draw boxes on a screen, connect the boxes, hit a button, and that would generate all your production code. Sounds incredible. I mean, could you imagine that sales guy walking in and saying, here we go? Okay, so let's just say it worked. Now, there was some badness with it because you ended up with 10 times as much written code as if a human would have done it. So you've really blown out your code base, and then you've made it hard for the humans to get in there to fix stuff. But now you've got a sustainability problem with your development environment. You have to move to every version of that tool to stay relevant. So it didn't get moved. So now you've got a chunk of code that you are kind of stuck with because it's in this proprietary model tool and you can't really move it forward and you're just stuck. So all that code's kind of throwaway now, which we never want to do. If we're writing good, solid, C code, we just need to repurpose it on other platforms. But when I really started thinking about MOSA, it is, and somebody had brought up, it was the difference between sustainability budgets and R&D budgets. And I think that is it's a gap that makes it harder. So from my perspective, when the initial MUOS ground system was delivered, I expected the refresh to start right away because we're engineers, we're humans, we're going to make mistakes. We need feedback from the field to then guide us on what to fix going next. And when that cycle of iteration doesn't keep going, the team, the tools, the operating systems, the components, everything starts to just gray out. So if we look at how we do it, we've been constantly developing a replacement MUOS ground system since 2012 with a very small team. So it's taken us longer, but we're there now.
Looking forward, what do you see as the game changer for MUOS systems, and predict the future a little bit?
The first game changer is once the MUOS ground system is refreshed, one of the issues is it's got to support all the existing terminals out there. So with a refresh, we can add capability to those existing terminals and it will feel more performant. We basically need to fix the way data is handled in the network to make it feel more like a 4G, 5G system. Now, the data rates aren't ever going to get monstrous fast, but for the individual user, it would feel better. Now, on the handset side, there is some incredible stuff happening. So it was really weird because if you think of how can you process a WCDMA signal, an FPGA is like the king. But with an FPGA, it likes a lot of power to do its job. So for us to shrink down what we've done, we've actually gone back to a DSP. And DSPs have really gone out of favor over the past couple of years because it seems like the big industry has settled on, I've got FPGAs for streaming type processing, and I've got GPUs for batch style processing. And then a CPU in the middle can handle everything else. But between those three, I can pretty much build a real-time processing radio. The DSP is really awesome, though, from a power constraint platform. So it's weird. Our MUOS ground system is more power efficient, handling multiple MUOS terminals than a MUOS terminal is. And it's because of the processors that we chose to run inside that system. It's harder to program, but there are some benefits to DSPs because it's bare metal. And so for what people don't know is that means there's no operating system. It's your code executing on that processor directly. It's harder to code, but then we don't have to deal with moving operating systems. So I know like in the life of the MOOS, we're already on our 4th operating system. Just going from Linux to Linux to Linux. But every time you make that jump, Linux has changed under you a bit. You know, the industry for those computers have gotten better. So then it's not a free upgrade. You have to go and rework stuff in that new operating system to get it to execute. So what I've been seeing is some of the new DSPs that are going to hit the market, and they're going to be incredible. I think it's going to change handsets for the dismounted soldier, just, you know, because right now the guys are carrying around 3 batteries.
Hey, if you could figure out a way to make a battery that lasts for a week, you'll make a lot more money than you'll ever make selling, you know, MUOS terminals.
No doubt. And you know, it's not my passion. I'm not going to solve the battery problem, but looking around YouTube, there's enough people out there trying to solve the battery problem. But it's kind of like a storage cabinet in your house. Let's say you had a blank wall and you go and you put a new storage cabinet on it. You're going to find stuff to put in that storage cabinet. So if we give people bigger batteries, they're going to find a way to use that energy in that battery for something. So I don't think applying a bigger battery solves the problem because we're going to always consume everything in it. We still need to be very conscious about what we put into that disadvantaged processing unit, the handset, the terminal. So, you know, and it's one of those things that I'm getting a little worried. So in this space, now AI is jumping in. And to say AI has a very streamlined, predictable processing path that's very power efficient hasn't happened yet. So if we're going to take AI and throw it to a soldier that runs locally, well, where are we getting all that power from? And now we're fighting his communication budget with his AI budget. But then the flip side to it, if you have MUOS and you want to use an AI chat client, it's perfect for that. I mean, MUOS does short messaging fantastic. So I think there's going to be ways to work with these new chips that are coming out down the pipeline, these really specialized DSPs, and I think they're going to make things way more power efficient. Then the last thing is, and this is, you know, I've been thinking, how does MUOS stay relevant in this day and age? We have Starlink, 5G NTN systems are going to start coming online, and none of them still fill the role of what MUOS was designed for. You know, triple jungle canopy, it's always got to work. The weather doesn't matter, it just has to work. And I think I'm finally starting to see it is this real embrace of IP connected networks. And for a long time, people would talk about it, and the military was trying to figure it out. And I think we're over the learning curve now for just distributed IP networks. So what that means is we need to allow all of these bigger networks, these systems like MUOS, it's the system-to-system communication now. How does MUOS on the back end interface with a 5G NTN system? Because what a lot of approaches that I see is people will take a 2-channel MAN pack and run their 5G NTN piece on one channel and then the MUOS piece on the other and then use it as a bridge. That breaks, Jason's rule 1. Don't ever put anything over a wireless link that you could easily put over a wired link. The RF spectrum's too precious to waste it that way. We need to do all those networking functions back at the ground stations and make it seamless to the user. So I think we're going to start seeing that, and it'll be seamless to the soldier. It's going to be easier for the soldiers because the networks will handle more. Remember, MUOS was the first attempt at a custom cellular network deployed around the globe. We learned a lot of lessons from it, and now it's to take those lessons and refine them to really meet what the soldier is looking for today versus what the requirements were 20 years from now.
That brings us to the end of our broadcast. Thank you, Jason, for speaking. I learned a lot today about MUOS that I didn't know. Really appreciate it. And thanks to all of you for attending today to this McHale Report podcast. I look forward to seeing you on future broadcasts.
Awesome.